Hi, my name is Bill Kinney. This is video number 51 in my series on arithmetic, algebra, and graphing. Part 10 of a subseries on algebra, formulas, functions, and graphing with an emphasis on spreadsheet usage. It's the fourth video where I'm using spreadsheets. In the last video we looked at an example where we were looking at the relationship between Celsius and Fahrenheit temperatures. Got a linear function is what this is called that gives us the Fahrenheit temperature for a given Celsius temperature, gives us F when we know C. We needed to figure out the slope of that function, the slope of F with respect to C, change in F, change in Fahrenheit temperature, divided by change in C, delta F over delta C. And we needed to find the intercept, 32 in this case, to help us find a formula. And then when we used Excel to get the formula, to actually evaluate the formula, we needed to use dollar signs to keep certain cell references fixed, in this case B12 and B13, and other cell references, B16 in this case, not fixed as we copy and paste down. As I said, the dollar sign in front of the B's keeps the column fixed, the dollar sign in front of the 12 and the 13 keeps the corresponding rows fixed, but just play it safe. Let's not worry about more advanced applications where you just do one dollar sign. Just play it safe and put dollar signs, in a sense, around the B in this case. Let's look at the graph of this. Okay, we'll just focus on the numbers this time. Highlight those, go to my charts, scatter. There we go. It's a lot of points there. It graphed a lot of points. Zoom out a bit. There's my graph of Fahrenheit, which would be on the vertical axis as a function of Celsius temperature. Let me go ahead and just label this quick. The vertical, which is the dependent variable. Here's the horizontal, which is the independent variable. I didn't really need to graph so many points because it was a straight line. Do notice that the vertical intercept is at 32. That's where it crosses the vertical axis. F equals 32. Do also notice that when C is 100, F is 212. We can estimate other values as well. The slope does tell us how steep the graph is. By the way, if I change the slope to being something else, the graph will get updated. I mean, this would be a wrong model. I'll change it to let's change it to 3. Watch the graph. Well, the scale changed. The visual slope didn't change much, but the scale changed. So the slope affects how much, how steep the graph is, though different scales won't necessarily affect the visual. If you change the scale, it won't affect the slope visually that much. And the intercept does affect where it crosses the vertical axis. I could change that as well. Did you see it shift down? I'll change back to 32. Watch it shift up. So there's a visual for how to interpret the slope and the intercept. The slope is the rate of change of F with respect to C. If I increase C by 1, F increases by 1.8. So for example, if I increase C by 2, F increases by 2 times 1.8. You can see 35.6 minus 32 is 3.6, which is the same as 2 times 1.8. That's a way to interpret the slope as a rate of change. All right, let's do another example on the next sheet. Suppose y is inversely proportional to x. Suppose further that y equals 2 when x equals 4. What is y when x equals 8, when it's 16, and what value of x will make y equal to 0.125? Y being inversely proportional to x means that the function here is of the form f of x equals some constant, called the constant of proportionality, divided by x. That's what inverse proportionality means. What is the constant going to be? Well, you can do some algebra, use the given information. When y equals 2 and x equals 4, plug in y equals 2 and x equals 4 into that equation, and solve for the unknown constant. you'll get the equation y equals the constant divided by 4, and if you multiply both sides by 4, you'll get that the constant equals 8. Instead of using the formula to answer the questions, which we could do, let's use a table of values. I can't plug in 0 in for x, though. That's something to be careful of here, because you'd be dividing by 0, which is not allowed. So I need to plug in something positive, and it's probably good to actually start with something like 0.1 and have it go up by 0.1 every time. This is going to make the table pretty big. What do I plug in for y? Well, it's the constant, which is in cell B7, which I want to keep fixed, divided by x, which in this first one is in cell B10, which I don't want to keep fixed, so I don't use dollar signs. When x is 0.1, y will be 8 divided by 0.1, which will be 80. And that's going to get updated correctly now. This is going to be a big table. Let's have some fun with it. Click and drag. Hundreds and hundreds of spots, maybe. Okay, I suppose that might be far enough. Well, actually, it's not going to be quite far enough to answer our last question. The last question is, what's x when y is 0.125, which is not quite small enough yet. Still not there. Keep experimenting. I guess we're answering the last question first. Oh, we're close. There it is. Y will equal 0.125 when x is 64. That answers the last question. What value of x will make y equal to 0.125? It'll be x equals 64. What about the other questions? What is y when x is 8? And what is y when x is 16? We can answer that quickly with the table as well. When x is 8, y is 1. 8 divided by 8 is 1. The formula is easy too. What is y when x is 16? 8 divided by 16 is 0.5. Y is 0.5. When x doubles, when x goes from 8 to 16, y gets cut in half from 1 to 0.5. That's a property about inverse proportionality. Let's look at the graph of this. How far should I go? Oh, I don't think I'll go all the way to 0.125. Let's just stop there. Charts. Scatter. Here we go. Kind of big. Let's zoom out. There's the graph. It's not a straight line. That's what typically happens with, well, that is what happens with inverse proportionality, is you don't get a graph that's a straight line. It's a curve. It's decreasing. Y goes down as x goes up. It's falling downward here. And it's also called concave up. It's sort of like part of a bowl shape, if you will. That's called concave up. It turns out that even though y goes down as x goes up, it doesn't go down as fast as you go further and further on, and you can see that here pretty clearly. It drops by 40 there, then by 13 1/3 there, then by 6 2/3 there, 4, etc. The amount that y goes down for a given increase in x is less and less, though it does keep going down as we go. So that's an example with inverse proportionality, and with that I'll end this video.